Hey everyone, welcome to the stream. I guess we are live. I am
Welcome,
Ritik,
welcome, welcome.
and joined with me today is again my colleague Orithro from PyImageSearch.com. So I'm just going to let everyone settle in, pause for a couple of moments here so that everyone can join in the stream and no one's left behind as we go on this journey. And while we wait for everyone to join in, it would be interesting to know where everyone is joining from, like who is joining us. So if you could comment down below or comment or chat us about where you're joining us from, then that would be pretty awesome.
Hello from India, by the way. I see people commenting. What's the topic? It's on transformers. A deep dive into it. From
Yes,
USA, from India. Hey friends.
Malaysia,
I see everyone
Texas,
joining in.
London. Wow. Um, okay,
Thank you for
Korea,
joining. Thank you for joining.
Slovakia. Thank you, everyone. Thank you for joining. We'll be starting in just a minute.
Yep.
So, just going to let everyone settle in.
I see Devjyoti coming in. I see Devjyoti. Devjyoti, I see you. ah, I see Turkey. I see Paris. Denmark. Hello, everyone. Hello. Thanks for popping in. So, today we are going to cover a lot about transformers. I'm just going to, give a disclaimer that it's going to be a long stream. So,
Absolutely.
take your time, settle in. We are going to cover a big topic, and it's one of our favorite topics.
Are we building
So,
Optimus Prime or Megatron? Good one.
I
We'll see.
think Megatron.
Yeah.
So yeah, disclaimers. Sit back, chill. Absolutely. It's a Friday, so it's a long stream that I know. And what would be best is if you could also have a glass of water lying around so that you could reach to it as soon as you can, because it's going to be heavy with a lot of topics. And what I would suggest, that this is my personal suggestion, is to have a notebook so that you could write down or scribble down notes as we go along, because we are not only going to cover the topics, but we are also going to cover a little bit of maths. Let's be honest, that's going to be a lot of maths. So while you are at it, uh, you can scribble it up. If you want some help from us, you could chat to us in the live chat itself and hold on to the thoughts. And yeah, that's about it from my end. Ritvik, do you
So,
have any? Yeah, go ahead.
yeah, two things before we get started. I see we are getting questions about already getting questions about vision transformers and swing transformers. Pretty advanced stuff. Excited that you guys are as into transformers as we are. But yes, we will be covering them, just not in this live stream. This live stream is going to be around transformers, and we will be we have some pretty decent surprises up our sleeves. I'm getting some questions about whether this stream will be available for viewing at a later time. Yes and no. uh, it will be available on our YouTube channel, but you won't get to interact with us, or you
Right.
won't get to ask questions about the things that you see on screen. So you are as much part of this stream as we are. So if you are not in the stream, then I think a pretty important ingredient will be missing when you watch it later on, which is going to be you. So I would really love if you stay on, ask questions, hop on a discussion with us. And with that said, um, this topic, as we saw from our poll, has been long time coming, and we are pretty excited about it, as you can say from the grin from Oritra's face. And I guess everyone around here has been excited for Transformers for the last 5 years. So I would say about time. And the way this session is structured is it's going to be a, a kind of fancy live journey through the multiverse of attention. Our spaceship here that you see on screen is going to visit these outposts. The pointers on screen are the outposts, and overcome certain obstacles to understand how transformers work. Our mission is to understand how each subtopic comes together to weave this wonderful architecture. So uh, this this is going to be our theme throughout the slides. So we as your co-pilots will be taking you on this journey, and we will be understanding how each of these topics work and how they come together, and how ultimately they all form transformers as we see from the paper. Attention is all you need. So that, and before we actually dive into the topics, this is something that we want to ask every one of you. So if you have a transformers project in mind or any computer vision project in mind, do let us know. And also, we think PyImageSearch University, PyImageSearch, the company that is bringing this to you, PyImageSearch University can help you here. They can. PyImageSearch University has tutorials or code that will speed up your project completion, because you will have ready-made code available. It will make your project more robust with high quality models, and it will make your project run faster at the edge with optimized code. So we spend somewhere between 10 to 12 hours working on a code for every project. They do not go out without quality check assurance, or pass going through us basically. So in no way will you have code that is sub optimized or does not run, or breaks every time you put it in a server or somewhere. It works and will work for you, and will make project collaboration easier with well documented code and comments. And we do take comments and documentation seriously, so it will be you wouldn't have to look at a certain line of code and scratch your heads for 2 hours wondering what it does. So anyone joining this live lesson will have access to 20% off on PyImageSearch University exclusively for the duration of this stream. So people who will be, putting this off for, saving it to bookmarks basically and checking in tomorrow or day after will not have that 20% offer. It is meant for people who are joining us in this journey, who are going on with us. And all you have to do to get 20% off is scan the QR code on the screen, and you will be directed to the page with the offer code applied. And I will just put the link in the chat. Meanwhile, Oritra, do you have anything to add?
Yeah. So, hello everyone who are joining in. Who are like, I see a lot of highs coming in. So, hi everyone who is with us. So, as Ritvik said, PyImageSearch University is a collection of courses, and these courses help you into getting into computer vision firstly, and also into understanding how things are. So, if you are familiar with PyImageSearch, the structure that we take into account is gradually increasing the complexity. So uh, it's never that we are always going to give you a complex topic and break it down. No, we are going to do it from scratch. So where did that topic come from? Where is say attention coming from? And then evolving attention into something that we get. And I'm sure in this live stream you are going to get a taste of that, because we are not only going to cover the paper called Attention is All You Need, but we are also going to cover some subtle things that are, at least I haven't found them in the internet lying around. So there are subtle things that we will be covering, and that might give you understanding of how PyImageSearch works. So scanning the QR will give you a 20% off
And
in
just
getting into
just
PyImageSearch.
to
Yeah,
yeah, sorry, Atra,
of
but I
course.
would just like to let people know that if you are already a PyImageSearch University member, then you wouldn't need to worry, because this is actually a sneak peek into a tutorial that is coming out, and you will have access to code, collab notebooks, video tutorials, all of the things that you generally do have access to. You'll have access to all of that uh, for you through your courses. So you do not need to worry about whether you will have access to this. This is for people who are on the fence about joining PyImageSearch University, or who might have a project in mind that they are not being able to finish up. So without wasting any more time, scan the QR code if you are that person, go to the checkout page, uh, take the offer and take the course. And it comes with a 30-day money back guarantee, so you wouldn't have to worry about wasting any money, so to speak. So with that, let's finally dive into the architecture. And you might be wondering, like, hold on a minute. A minute ago, we were talking about the how we are all excited about attention, and how transformers is an exciting topic, and now we are going into the architecture head first. Well, this is going to be special, because if you look at the if you look at the architecture, or if you get a sense of what you are doing, what the architecture is, then later on, as we go through those specific topics, then you will be able to understand that better. So this is the entire transformers architecture. And we take a top down approach in building the intuitions behind the transformers architecture. So let us first look at the entire architecture and break down each individual components later as we go along. And also, if this diagram is not visible to you, let me know if you want me to zoom in and show the diagram with better clarity. Let me know in the chat if it's visible to you, if you want me to zoom in. The transformers architecture that you are seeing on screen basically consists of two blocks, right? Two. Okay, I
I
think.
Yeah, I think we need to zoom in.
Cool. Hold on a second. Is it visible?
I think we need to zoom in a little.
Yeah.
Yes, yes. Let us know that
So,
it's. Let us know in the
hey,
chat.
David, good to see you.
Hey, David.
Right. So, this is what the architecture looks like. And well, basically, what this architecture comprises of is two major building blocks. And we can see these two building blocks in kind of yellow and purple over here. This one on the left is called the encoder, and this one on the right is called the decoder. So these are the two blocks that comprise of that basically build up transformer. And majority of our time here, we are going to be talking about every little component inside these blocks, and also how some of those components evolved. So I guess this is clear right now.
Right. Yeah.
Right. Cool. So I will move along. Sorry for that. I will move along to the next part, which is the encoder. Now, the encoder, basically as shown in the figure, is comprised of n identical stacks. So this is the encoder, and it comprises of n identical layers. Each layer is composed of two sublayers. The first is a multi-head self-attention layer, and the second is point-wise, fully connected feed-forward network. The authors also employ residual connections, as shown in green, and normalization operation around those two sublayers. We will learn, and you might be thinking, like, what is happening right now? I was just told about transformers. Now I'm into the transformers encoder. Now we are talking about attention, multi-heads, normalization, what is happening? It's going all over. But do not worry. All you need to remember right now is that this is what encoder looks like. And there are two things, the multi-head attention and the feed-forward network. And there are two other things, normalization layers and residual connections, that are tying them together. What they are and how they work is something that we are going to cover in the following, in the time that follows, right? So just remember, for the time being, this is what encoder looks like. And similarly, this is what a decoder would look like. And a decoder is exactly similar to what the encoder is, with one small minor addition. In addition to the two sublayers that we saw earlier in the encoder, the decoder inserts a third sublayer which performs multi-head addition over the output of the encoder. So this is the output of the encoder, and this comes in, and there is this one third sublayer which is inserted, which performs multi-head addition on the output of this sublayer, on the output of the encoder. And it also has residual connections and normalization layers, and there is a feed forward network as shown in the encoder previously. Now you would also notice that this right here is not our same, is not the same as this layer over here. So this layer represents multi-head attention, and this layer represents masked multi-head attention. So the decoder, two things to remember here: this is what it looks like. It has one addition, so one multi-head attention layer is coming in and is taking inputs from the encoder. Now, another thing is that the very first attention layer is a masked multi-head attention layer. It is not a simple multi-head attention layer, right? And the reason this is laid out in the beginning is that you will, as as you reference it to information that you get later on, you will be slowly able to understand and process why these components have been chosen, why specifically mask multi-head attention, and why specifically output from the encoder that is coming in to the attention layer. And that is it. That is basically what, just give me a moment.
While he zooms in and zooms out of the screens,
Yeah.
let me take over for a little moment and just let you all know that there were a lot of jargons in the first couple of slides, because we are going to cover the architecture in and out. So the first thing that always helps is to throw the entire architecture on your face, for a lack of a better word, and slowly take down the entire architecture and strip it to pieces, and then talk about them. So what we really wanted you all to know is that this architecture has a lot of layers, right? Sublayers, multi-head attention, mask multi-head attention, one is self, one is cross, blah blah blah. But what we want you to know from these couple of slides is that the architecture has a lot of sublayers, and we don't have to, you know think about it all the same. We will come to each and every sublayer uh, later in the slides and in the recording as well, and then weave it back again. So firstly, we see the architecture as a whole, we strip it off to pieces, individual pieces, we talk about the pieces, and at the end of the slide we weave it back together, and then we pose the question, how familiar are you with transformers? Does that make sense? Right. And
Right.
Ritvik, you can go ahead.
Absolutely. So I guess we are done with the architecture, like the initial parts of what the architecture shows, and this is where we were at. And what we are going to do now is we are going to go over what attention is and how attention evolved to the current day, or to the version that we see in the paper attention is all you need. So, Audra, I would like to hand it over to you at this point. Ask
Yep.
you like, what is the story? How did attention evolve, and where did it all come from?
Right. So this is the first step of stripping down the entire architecture. The main building block of the transformer is, as you all know, or if you don't, I'm letting you know, is attention. So what we will do in a couple of slides is that we'll talk about attention as in what it is, and then we will slowly evolve our basic building block, that is attention, to what we will have in a transformer, that is multi-head attention, be it self, be it cross. So moving on to what we are going to do is that we had, as you might know, we also had a live stream a month back on neural machine translation. So neural machine translation is a task where we have an input sentence or an input with a different language, and a target sentence with a different language, and we try to model our you know RNN model or LSTM models or anything which can model the input and target sentences individually, so that upon giving an input sentence it can translate it to the target sentence, right? So with that, we also let people know that there is a concept of attention with Luong and Badenau's attention, which can be swapped in, or just it's a plug and play kind of a module that can go into the RNN or LSTM model that we have, and it works pretty well. Now in 2017, Vaswani et al., that is the authors of Attention is All You Need, tried tackling neural machine translation, that is input sentence to target sentence, without any recurrence, that is no RNNs, no LSTMs, without any convolutions, so no convolutions either. They took the attention module and they said, we are going to use attention and only attention, that is it, and it works. And you might know, it's 5 years down the line, you might know transformers are everywhere. uh, in any research paper that you can take up, you have a transformer model in it. So the evolution of Badenau's attention or Luong's attention, from that into the masked multi-head attention, or just the multi-head attention that the paper, that is Attention is All You Need, proposed, is the evolution that we'll be talking about today. So the first thing that I wanted to ask you is that when you are given a scenery, say this is a scenery, and we say a query, or we query where is the land, the first time your eyes go to this section of the image. So you are attending, quote unquote, air quotes, attending to the land. And when I say sky, you're attending to the sky, right? So you are masking out the unnecessary bit with respect to what we are asking you. So the land, when we say land, where is the land? You are masking out the sky, and when we say sky, you're masking out the land. So that is how attention works. It's fairly simple. You have a query, you have an image, or maybe input. I'm not saying image. We love images. We are a computer vision first company. We love images. But it might be a sentence, it might be audio, it might be anything,
Any
any
tokens?
modality,
Any
right?
tokens? Yeah.
Any tokens for that matter. And we give you a query that is, where is the land? And you quickly attend to parts which have more information with respect to the token, and you quickly mask out the part which does not have what you need with respect to the token, right? So always remember, we have an input and we have a query. The query is where you are going to attend to with respect to what you're going to attend to. So keeping that in mind, we'll quickly move to version 0. So what is version 0 and what are we going to do? Just a little heads up is that we are going to have a flow diagram of how attention works. So if you know how attention is all you need paper is laid out, you'll have an attention term, which is qk by root dim softmax with v. And this is too much for now. But what we'll try to do is, we are not going to go into the math right now. We'll do it visually, because as we think, uh, it's far more helpful to do maths in a vision first or visually first manner. So what we'll do first is that we'll have an input matrix that is X and a query matrix that is Q. And we'll call it query vector because it's not a matrix yet. It's just 1D matrix, which we call a vector, right? So the shape, think about the shape of the input matrix to be NX and DX. What is NX? NX is the number of rows that this input matrix has, and DX is the dimension of each row, right? Or you can call it the number of columns, but we like to call it as the dimensions of each row. And DQ is just that query vector dimension. And these two are like the query that I made just a slide back, that is land, and X can be thought of as an image. It is not an image, it can be thought of. I'm trying to build an analogy here. So it's not an image, an image will have different channels and all that. We are not going into that. What we are trying to do is align our analogy of land and sky and how to mask and how to attend, and try to figure this out intuitively. So again, we have X, we have Q, and both of them go into a function called f of ATT. This is a generic function. It can be a dense network, it can be a dot product, it can be anything. It's a generic network which takes in our DQ or the query vector and the input matrix, that is X, and it gives you another matrix which is the E matrix, which is called as an energy matrix. So what happens with an energy matrix is that uh, it tells us, as in the ones who need the attention weights and attention scores and all that, it tells us that in X, which are the rows that are very similar to Q, right? So with think about that image again. So you have the sky, you have the land, and when I say a query, say land, you say that okay, in this part of the image, this is where the land is, right? So it's very similar to what our thoughts of the query vector is, right? So the Q and X going into the f of ATT gives you E, which tells you which of the rows of X, that is input matrix, is very similar to Q, or or in other words, what is more important to Q in X, right?
So,
So say,
Arthur,
yeah, go ahead.
just before we move ahead for
Mhm.
our viewers, what exactly is FATT in this case?
Right. So FATT is just a generic function right now. So we'll not get into the function itself, as in we'll just consider it to be a black box which takes
That
in
computes
inputs.
attention.
Right, exactly. It just computes the energy matrix. We haven't arrived to attention yet.
Right.
We'll just take it to the energy matrix. And why am I saying energy matrix? Because that is the matrix that tells you which of the rows of X are are more important to Q and which of the rows of X are not important to Q at all,
Right.
right?
Right.
And now once you think about it intuitively, when you pass this E into a soft max operation, what happens is you get a distribution, or you get one row or the elements that are more important, and all the elements that are not important are go to zero, like close to zero. That means we are now approaching to a vector which will have elements of X that are very highly needed for the query, and also the elements of X that are not needed at all. So think about that analogy again, an image with sky and land. Once I say land, you also mask out the sky, right? It has to go to zero. You don't need that information. You just need the land because that is the information that you need. So thinking about that again, so the softmax helps in doing that. Softmax is always going to give you a distribution where the elements that you really need are close to one or maxed out, and the elements that are not really needed with respect to the query kind of go close to zero, hence helping you to understand, okay, these are the elements that I need, these are the elements that I don't. Does that make sense, Ritvik? I'm going to
It
stop for a while.
absolutely does. It
I'm
absolutely
going to
does.
yeah, I'm going to stop for a while and look at the chat. If Let me know if this makes sense, and only then will we go ahead with different versions, because this is the crux of the entire attention formulas. We really want you all to understand what we are trying to say. It's not only about attention. Attention is not only about taking up the important characters, but also masking out the not so important characters. So softmax will have that character inside of it. So I'm going to see the chats.
So Mariama has a question about,
Mhm.
you talked about query key value, but we
Right.
only see Q here, which
Mhm.
is the query. What about the other two? Very sharp question. So
Very sharp
I
question.
think
Yes.
what I am going to, so here Q is query and X is image. Well, Oithra was trying to put an analogy about the
Mhm.
image being a scenery, and you will have land and sky, so you will attend to different parts. But X is basically your input. So in our case, or in the case of the original paper, it is sentences which will be translated to another sentence, right? And to answer the previous question, what about the other two? Where is K and V? Well, K and V does not come into picture for much
In
later
version
on.
0.
Yeah. So basically, if you think about this intuitively, and we think about that picture of a scenery with sky and land, what you initially had was uh, your input, and which is a scenery, and your question. So how is the sky, or what does the land look like? So you have a question and you have an input. You do not have those segmentations of key and value yet, so we'll have to formulate them, hopefully, as we go ahead.
And I
So
also
also,
see a really good question. Shouldn't DQ be DX? And that's a really sharp question again. And I thank you for that, because in version 1 that is the case. So that was my segue into getting to the next slide. So I hope this is going to be answered in version 1. So what we do in version 1, I'll click again and highlight. So we swap out our f of att, which was a generic function, to a dot product. And remember what I said is that we need our energy matrix, that is E, to tell us which of the rows of X are very close or very similar to Q, right? And the dot product, if you think about it, does exactly that, right? And Q will be dot producted with X, and it will be broadcasted, absolutely that. So it will be broadcasted into E, and E will give you the same intuition, that is, which of the rows of X are really close to Q, right? With the dot product. And due to the fact that we are taking a dot product, it is very important that the shapes of the query and the input matrix aligns. So now, to the question, D of Q is the query, is the shape of the query, and we change the input matrices dimension to be D of Q, so that both of them align and can be passed into a dot product. I hope that the answer is justified. And as highlighted, we also make this change. So we will go on highlighting what are the changes as we move into other slides, like other versions. And yeah, everything else remains the same, not going into that. So Qx goes into a dot product. We get our energy matrix E. We again pass it to softmax. We get our attention weights. We multiply our attention weights with X, that is the input, and we get a output Y, which now tells you that okay, these are the only elements that we need, because this was our query vector. Due to Q, we are going to have a Y. So every other Q, that is, if we change the queries, if we say from sky to land, the Y will change. That is, the output will change, right? So moving from version 0, we had a basic structure of how attention works. We have a query, we have an input, and a bunch of things happen. And now we move on to version 1, where the f of att, that was a generic function, is swapped into being a dot product. Everything remains the same. Now we start with a problem, and this is my favorite part into understanding how we go from version 1 to version 2. Version 2 comes a little later, and version 2 is kind of the heart of the paper. Attention is all you need, but it is not quite talked about. So what we'll do is, we'll understand a problem first. We'll ask you what the solution could be, and then we will move into version 2. So the problem now here is that, and this is not a problem of the architecture. Let me get this straight. What we are going to cover in this section is not a problem of the architecture. It's out of the syllabus. It's just something that we wanted to do, and then we will come back to this problem again, right? So create a distribution with mean 0 and standard deviation 100. This is a normal distribution. A is a normal distribution. We can make a distribution with our numpy package, and then we visualize the histograms, right? And with while visualizing the histograms, this is the histogram that we found, and you can see that I have taken sample size of 10,000 just to make the histogram tighter. It has got nothing to do with how the histogram is going to look. So we plot it. We have a mean of 0, we have a standard deviation of 100, and we have a size of 10,000, and we plot the histogram. Now, what happens when we pass this normal distribution into a softmax, and how do we see that softmax? So can you see that it's just one peak and everything else goes to 0? And let me ask you this. Let me ask my audience this, and you, Ritvik, as well. He knows the answer. It's no fun. Let me ask you this: why is it, or why can it be a problem in any architecture that lays around? Softmax is something which we already use. In where do we use softmax? That is another question. Most of the times we use softmax to have a categorical distribution, right? And we also use a categorical cross entropy to compute the loss if we are doing image classification and whatnot. And if a softmax is so peaked up and the other elements are all zero, or go to 0, what is the one thing that is going to hamper? What is the one big thing that will harm our neural network? And I'll stop for 2 to 5 minutes. We'll talk about this, and we will check the chats as well. uh,
We're getting a lot of questions about images.
mhm.
The image was, I would like to repeat this again. Image was just for visualization and for creating an analogy. It wasn't that this version of transformers takes in images, or you can actually feed in images to this version of transformers. It is possible to have images go into transformers, but you will have to have a different kind of architecture for that, which is called vision transformers. And the processing to go inside that architecture is a little bit different. And hopefully, we'll cover that in a future live session and a tutorial. But for now, just think of X as an input, and your input can be, anything from uh, input sentences to time series data or whatever, as long as they can be tokenized.
Right. And so Ritvik, I also see a comment from Andre. Dot products would not produce energy vector, would produce energy vector, not a matrix. And I am sorry about this. I'll go back and denote where in the problem is. And I'm so thankful for Andre to point it out. We made a mistake here. It should be a vector and not a matrix because it's a dot product. So I am sorry, and thank you, Andre, for pointing it out. And everything else remains the same. We just need to swap it out with a vector. So thank you again. And yeah, this is a problem that we should have noted or noticed before going live. So yeah, I also saw Saurabh saying very low gradients on most places. That's really close to what the answer is. And I'll quickly move on to the solution, or maybe provide more context to what the problem is. So think about it. If you have a softmax which is so peaked, right, at this point, which is peaked, and everything else goes to 0, When we backpropagate, or when we backpropagate the gradients, what really happens is the gradient at that point is going to get backpropagated, and all the other gradients are going to get multiplied with zero, and hence we are not going to have all the weights of the neural network update as such. And this is called as a vanishing gradient problem. This will happen in if our softmaxes are really picked up. So, okay, Aurithra, I understand. We have a normal distribution, we have a standard deviation of 100 and mean of 0, and we plot a softmax. What is, yeah, okay, we understand that. Why do we need it? To understand the problem, as in the softmax and the backpropagating gradients not getting backpropagated well enough, we also come up with a solution, and we will talk about why we need it in the architecture or in the transformers architecture a little later. The solution here to get a better softmax is to scale down the standard deviated, like the 100 standard deviation normal distribution, into a unit standard deviation distribution. So what we do is we just scale it down with the standard deviation, and everything falls into place, as you may see in the next slide. So with the standard deviation 100, the softmax looks like this, and with standard deviation unity, the softmax is better. Can you see that the softmax does not change much? As in, the peak still remains at where it should be, just that now the softmax is better. It does not suppress to zero. It has values. Hence, the gradients will backpropagate better, right? And think about it. Think about version one. We have a softmax right inside our attention module, right? And if we are not taking care of this entire problem, that is the softmax being peaked, and we don't take our normal distribution, or the distribution that goes into our softmax, we do not take care of that, it will eventually lead to vanishing gradient problem, or vanishing gradients inside of the attention module itself. Not talking about the entire, and not talking about the entire transformer architecture yet. It's just going to create the problem inside the base, or the foundation that the transformer is built on, and that is a problem. So to help us with that, we just have to scale the entire distribution with a factor which turns out to be our dimension of the energy matrix. We just need to scale them down. So if you look at the paper, attention is all you need, we will have a root over dimension term that is being added on top of the dot product of q and k, and that will give you a scaled softmax. So everything remains the same. We have a scaled softmax, and eventually, once we do that with version 2 being completed, and we have a scaled softmax, I'm sorry, we come to a point where we can do this not with one query vector, but with a query matrix, right? We can do it. We can take a bunch of queries. We can take a bunch of inputs, and with the help of the linear algebra gods, what we can do is we can do a dot product of the q and x, and we can have a similar energy matrix. We can have a similar scaled softmax. Now we have an attention, not a vector, but an attention matrix. And again, upon applying that attention matrix to the input, we have y. So I need to stop right now, because this is the time when I go back and revisit what are the things that we covered. So version 0 covered a very generic framework of what attention is, what attention can do. So we had a query, we had an input, and we had a function called f of att. Then we have an energy matrix, or an energy vector. Thanks to Andre, we have an energy vector, and that goes into softmax. We have an attention vector, and that again gets multiplied with the input, and we have our output, which is how much of our information is needed from the input with respect to the query. That's it. Version 1 swapped out f of att with dot product, which helped in doing a bunch of stuff more efficiently. Version 2 talks about scaled softmax and why we need scaled softmax. We need scaled softmax so that the attention module does not face the vanishing gradient problem. It's as simple as that, right? And now with version 3 coming in, we have uh, with the help of linear algebra, we can now do parallel processing. That is, we have the query vector, we have a query matrix, we have an input matrix, and we can do a bunch of operations parallelly, right? So that with that we complete version 3. And I'm going to ask my colleague Ritvik, do you have any comments, do you have any thing that we want to talk about?
Not particularly, no, but I'm looking at some of the chat. I don't
Right.
see any questions. I don't see anything pertaining to the versions that we talked about. So I guess
Right.
we are safe to move ahead
Cool.
with the next versions.
So now, I think the first question that we had come across was from Mariama. If I'm mistaken, I'm sorry, but the question about query values and keys, we hear you, and this is version 4, where we try to talk about the QKV part of attention. So everything remains the same, just that we have two new matrices, that is a key matrix and a value matrix. And why do we need that? So think about a very complicated problem that you faced somewhere down the line in your life, right? The first approach that we always do, most certainly do, is break the problem into simpler chunks, right? And we want to have we want to tackle different simpler chunks first, and then tackle the entire problem altogether. That is what I do. It might help you, so think about that. And with key and value coming in, that is exactly what we are trying to do. So what we had previously is just one matrix, that is input matrix, which took care of the dot product as well as the multiplication that happens with attention. So previously what we had, I'll just go to version 3, is that x not only went into the dot product but also went into the multiplication operation that happened with the attention matrix. So it does two jobs all by itself, right? And think about it, when you are going to backpropagate the gradients, it's going to get two parallel gradients to it. One gradient is going to come from this section, right? And the other gradient is going to come from this section, and that might be conflicting gradients. So in a very hand wavy gesture, two gradients coming in, maybe that x might just be well off into taking one and only one gradient. It does not need the other gradient, or it needs the other gradient and not the previous gradient, right? So it just needs to take care of the two gradients separately, and that is what we do. X is now projected and linearly projected into K and V, so that K takes care of this dot product and V takes care of this matrix multiplication with the attention scores or weights, right? So what happens here is that due to the fact that we decoupled the complexity, we see that there is a better learning into the entire attention module. So going back to what I said, we have query which comes from the query land. We have an input matrix which we are going to linearly project into K and V, so that they can take care of the entire things and does not have to come to X altogether. So K learns individually, V learns individually, and both of them upon learning give some values to X for X to learn, right? And that is what happens, and which is version 4. And I might also mention that version 4 is also commonly called as the cross attention. Why do we call it as cross attention will be very clear with version 5. Version 5 are version 5 is where we okay, I just stop for a second because I saw a comment where I'm asked when you say linear projection, what's happening here. So I'll go back to version 4. What I mean by linear projection is that we just have a weight matrix which is being multiplied to x, and we project x into a different latent space called k. So
And
it's
you'll
just a,
see that in a moment. You'll see that happening on screen
right.
live.
And yeah, I'll just leave it to there. We will be seeing that for sure.
Yes.
So version 5 is where we talk about self attention. So version 4 was cross attention, version 5 is self attention. And what is self attention is that the query, which was coming from the query land, is now coming from the X matrix itself. So it's kind of philosophical to understand self attention, where you attend to yourself to find a better you. And that is entirely what is happening. So X is also providing is linearly projected to Q, is linearly projected to K, is linearly projected to V. So query, key, and value. And now does it make sense to call version 4 cross attention? Because Q does not come from X. It comes from a different domain, maybe from the decoder, maybe from the encoder, we don't know. It just comes from someplace else. Hence, it is cross referencing to the input matrix. And self, because X now takes care of this Q, right? So everything that you see Q, K, V comes from this sole input source that is X. And that is why we call it self attention, right? So with that, I'll let us take a break. If you want, you can have a quick run to your kitchen and grab a cup of coffee, because there are a lot of slides left. And just before that, it's just good to mention, because people have come in from different places, come in at different time. So do you have a transformers project in mind, or maybe a computer vision project in mind? If so, we can help. We are here to help. At PyImageSearch University, we have a lot of courses that can guide you, and we are currently coming up with a course on transformers, which talks about a lot and lot of things, so that it's intuitively very easy for you to understand transformers. You can write a research paper out of it. You can understand different research papers, and
Or put
also
it in production.
put it in production. And we are also going to understand uh, we are also going to let you know that we have provided full blown code for transformers in our courses. It's not just what we are doing right now without code and giving you the intuitions. Yes, we do that a lot, as in not code but intuitions. But we also have code in our courses, and you can just look into the code. It's in TensorFlow Keras, it's in PyTorch as well, so you can just jump in the code, look for it. How the code works is detailed, thoroughly detailed. If we are the instructors on transformers, you will find these two faces again popping up in your monitor, talking about the different things that transformers can do, and also the code. So yeah, go check it out. And for that, we have a 20% off exclusively for this stream, for people like you who have joined us. Don't come back to this later, because this is not going to be a lifetime thing that is going on. It's a 20% off, which
for
is a great deal
for
for
people
this.
who are joining in today.
Yes. So go check it out. Scan the QR. We'll keep this slide for a time now, and
And we are being asked whether we have courses about GAN like
we do.
transformers. Yes, we do. Uh, do join in, check them out. Um, Also, I think, Orithro, you are getting a lot of questions about scaled softmax. So while people
Right.
stay on the screen and they are able to scan this QR code, could you maybe go over scaled softmax again?
Right, absolutely. So I'll just keep this slide as is. We'll talk about the scale softmax in a very hand wavy gesture. So everyone, me, look at me. That's that's where you will get all the hands and gestures. So what we have is as we noted, that we have a softmax, which gets as input the energy matrix, right? And we all know that what this energy matrix and softmax does, it creates the attention vector, right? And what happens, and do you remember the slide on the problem? The problem was that if you have a very large standard deviation of a distribution, and you softmax the entire distribution, you're going to get one peak, right? And that peak is not really something that we want. Why do we not want that peak? We don't want that peak because it prohibits other gradients, that is gradients that are not peaked, to not flow into the entire back propagation stream, right? And that is not something which we want, because vanishing gradients are bad for a deep learning engineer, very very bad. So the how to solve that, what we do is we scale that distribution with the standard deviation itself, right? So on scaling that distribution with a standard deviation, what we get is that distribution itself, right? And that distribution itself, but the standard deviation now drops to unity, it's scaled down to unity. And with that, what we have is, when we pass that unit standard deviation distribution into a softmax, we get these peaks, which are important for our backpropagation to happen, right?
Basically,
So,
if you
yeah,
have one single pick, it will do nothing for your gradients. Like, for example, your gradient. So a gradient is what? Your measure of change, right?
right.
So if you have
Sensitivity.
one, yeah. So if you have one peak and then nothing else for miles and miles, you will have a very bad gradient, and your gradient
Right.
will basically vanish, cease to
Mhm.
be. And if your gradient vanishes, what happens to your loss? Now we go back to our deep learning fundamentals. The fundamentals are everything. If our gradient vanishes, if we do not have any gradient, what happens to our loss? It basically, it blows off. So your model will be fired from the get-go. So
It's
to
not going to get
prevent
updated
that,
because we don't have any sensitivity values.
exactly,
The Right, the neural networks are nothing but some a bunch of knobs, as Andrew Task quite rightly writes in his book, The Grokking Deep Learning. And big shout out to him. That book has basically founded my entire, understanding of neural networks. So it's a bunch of knobs that you can tune. So once you have these gradients coming in, if you understand the gradient, you understand how much do you have to tune the knobs. If you don't have gradients coming in, you don't know where to go. So
exactly,
as Ritvik rightly said, it's going to fire your neural network from the get go. It's not going to update at all, and it's not going to give you what you're asking it to do. So what here happens is, with the scale softmax, can you Ritvik, can you go back to the previous slide just a little?
yeah,
Yes. So what happens here is that, with the peaks all coming in, with standard deviation 1 or unity standard deviation, every gradient gets its sensitive gets to go back to this, what do you call it, to this knobs, to the weights. The weights now know, okay, I know this is the, excuse me, I know this is the amount of this is the amount of sensitivity that I have on my loss. Hence, I'm going to tune in this way, this much, and every weight does that. Hence, we need a better softmax for the weights to, or for the gradients to backpropagate properly. And Ritvik, could you go to the slide with the scaled softmax? Right. For this, what we do is, we'll just go over this code quickly. A is a random normal with 0 as mean and 1 as its standard deviation, and B does the same. So A and B are normal distributions with 0 as mean and unity, what do you call it? Standard deviation. Yes, I just forgot. For a moment I was blank. Like, what is it? What is it not coming into my head? So A and B does that. And with C, what we have is, we have those dot producted. So think about query and key as A and B, which have good standard deviation. One standard deviation is always a thumbs up. 100 standard deviation is never something that we want. So A can be thought of as a query, B can be thought of as our value, or sorry, key. So both of them have good standard deviations, that is unity standard deviation. And now C is thought of as our energy matrix, not a matrix. Again, thank you, Andre. Not a matrix, a vector, which has the np dot ab, that is the dot product of the entire key and query, right? So once we have C, if we do a np dot mean, we will see that it is more or less near to the mean that we had with a and b. But upon seeing the np dot standard deviation of c, can you see that the standard deviation has increased from unity to 10? And why is it 10? Because the variance goes to 100 and the standard deviation is just a square root of the variance, right? As far as my mathematical skills go, that is what I have been taught in my calculus lessons. So that is what happens, or in my statistics lessons as well. So what eventually happens is, why do we have this term 100 or 10? Look into the size of the random distributions. A has a size of 100, b has a size of 100. So that is the dimension of the query and the dimension of the key. So once you note that, okay, I have good vectors, but when we dot product those two vectors, they have a bad standard deviation. And how do we get out of that bad standard deviation? We scale it. But okay, Aritro, I know that we need to scale it. What do we scale it with? We scale it with the standard deviation of c, that is 10. And how do we know that what is the standard deviation of c? We know right now in this slide, because we have provided those details. Like, we know that it's a size of 100, we know that it's a size of 100, hence the variance is 100 and the standard deviation is 10. But in a generic fashion, we know that d or dimensions of a transformer or the attention module is something that is known to us, that is called d of q or d of k or d of v, right? We just need to root over d of k, and that is basically it. So I'll quickly and Ritvik, if you have any pointers, you can go ahead and talk about it. I'll quickly bring up that equation, just that equation, where we scale it in my tab, and it might take a while to do that. So if you want to talk to our audience, please feel free.
Um, no, I'll wait for you to bring up the
Okay, cool.
equation. I guess we do not have any questions at this moment.
Okay,
And
right. It's just going to get loaded, like the archive link.
absolutely.
It's just going to get loaded, and
So as Arthur was
yep.
mentioning about the scaled softmax, what is equally important to understand is why what solutions were provided by the scaled softmax and
Mhm.
how it evolved into the current form.
Right.
So
And I
I
also
think
have
this
this.
is
Yeah. Exactly. Thanks, Ritvik. So, attention QKV. Can you see there's root over DK? And this is something which they also mention why they have put it, but I didn't find this explanation quite intuitive. Hence, I made my own distributions, took their dot products and all that. So this is the scaled term that is going to scale the q and k transpose, that is a dot product, essentially dot product of query and key. And then we are going to use this scaled term and pass it into softmax, and hence we call it scaled softmax. So does that make sense? Does that make more sense? Let me know in the chat. I'm looking at the chat here and there. So yeah, that's about it. You can I will close this tab. Yes.
so I guess that was a long detour back from where we were at, and we were at probably this version of transformers,
Yeah,
this
version
version of
5 was
attention.
complete. Yep.
Yeah. So version 5 is self attention, and version 4 was cross attention. And we also had a little bit about how inputs were being projected. So we are now going to look at how inputs were being projected and what does linear projection actually mean. So before that, we actually have to finish our journey into the final version of attention, and well, this is the final version that the authors propose. And if we look at this figure, now this figure is a completely different figure from this one, but it's also not so different, and we'll go through it together. So basically what is happening here is can be broken down into three parts: split, attend, and concat. So you have to split the input, you have to attend to the parts of the input, you have to concat them, and then you have to project them. The reason behind splitting is the authors wanted to decouple, or as Arithro rightly mentioned a couple of minutes back, they wanted to break down the initial input into chunks and feed that, propagate that forward. What that does is it you know slacks off, or it shifts the onus from one particular matrix or one particular input into three segments. So that's what we do, right? The in very fancy terms, it can be said as decoupling the relations and then introducing multiple heads of attention, right? So this means that the key value and query matrices are now split into number of heads. You can see the number of heads over here, and they are being projected. The individual splits are passed into a self attention module. So we learned about self attention a while back, and all the splits are then concatenated into a single representation. So split, attend, concat. That's all that is happening. And this is the very simple representation of multi-head attention. We learned about where it came from to what this like simplest uh, way of representing attention could be. And now to our initial itch, which was how are they getting linearly projected. So we have actually built this animation, and this animation has been built programmatically using Python. So there's a library of Python called manim, which stands for math animation. Huge shout out to that. It was created by Grant Sanderson, who is also popularly known as 3 Blue 1 Brown. You can check out his channel as well. So this is a animation of what happens for projection of inputs, and I'm just going to let this pretty animation play out for a while, and then we'll talk about it a while.
Right. We can also let people know about whether you want us to, go into talking about manim, because these are all code based animations. We can also open
Absolutely.
source. We can open source this code if you want to further, go into research. And what we find most interesting is that um, the amount of communication that can happen on visualizations is huge. So if I talk to you about projection, it makes sense. If I talk to you about projections in a slide, it also makes sense. But if I just throw out this visual in front of you, it will definitely make sense, and it's just what I am thinking will come to you. So if
Absolutely.
you are really interested in writing blog posts, if you are interested into teaching or maybe research, let us know. If you want us to open source this code, we can from PyImageSearch. If you want us a blog post on this, we can write that as well. If you want a blog post on different topics, let us know. We are active on all socials, or you could also comment down below. So yeah, Ritvik, you were saying.
Yeah. So basically, we have paused at this moment, and what is happening is our input. So our input, which is represented by matrix I,
Hi.
is going to is basically falling down upon our another matrix called WQ, right? And the
Mhm.
matrix placed right below I, or our input matrix, is the weight matrix for query, which is why it's called WQ. Now, as it gets multiplied with WQ, we get another matrix called our query matrix. So that is how it is getting linearly projected, and we see the same process play out for key with WK and value with WV, and they are all different weight matrices, and the input is projected through each of these weight matrices or multiplied with each of these weight matrices to give you query key and value. That is what linear projection means. And they are represented on screen with red, green, and blue uh, to, to further illustrate the point. Um, Moving on, Auditra talked a while about cross attention or version 4 and what exactly is cross attention or what happens inside of cross attention. We saw that figure or we saw that diagram of version 4, but we are yet to see it play out in real time. So again, I'm just going to lay this animation on
And I'm going
for
to
a
comment
while.
on that.
Yeah,
Yeah. So we started from query, key, and value. And Ritvik, it would be great if you could stop at certain points where, yeah, that's the best. Yes, it's the
yes.
best part we can start off with. So we had I, that is the gray matrix. We projected it into query, key, and value. And the second animation starts from query, key, and value, right? We
So
have the query matrix, we have the key matrix, we have the value matrix, and we'll let it play.
right. So query and the key matrices gets multiplied. Notice how the
Right.
key matrix rotates
Hmm.
before multiplication. That is because during a matrix multiplication, you will have to do a transpose and you get something called QK product, quite originally named. And we as we do with as we did mention a while back, we scale the QK product term with 1 by root over of dimension. That is to prevent the vanishing gradient problem, as Arthur mentioned twice. And we finally get a scaled QK product term, which we pass through the softmax layer. And you see that at this point we have the scaled QK product term, which is like has all uniform yellow squares. But as it passes through the softmax, what it does is it highlights certain areas of that matrix and other areas are completely blacked out. So some areas will have intensity and while other areas will have lesser intensities. And that is what softmax does, right? It basically gives you a probability or a distribution based on your input. And that softmax output of the scaled QK product term is then multiplied with the value matrix. Yes, we haven't forgotten about our value matrix that we have split and we have kept aside. It gets multiplied with the softmax output to give us the, wait for it, final attention output. And that is, and what you just saw play out on the screen is is what is what attention or cross cross attention does, right? And that is the essence of what version 4 has to offer. So with that, Arthur, do you have something you would like to say at this point?
Just a little caveat is that the paper equation that I quickly shared uh, is what is being animated here. So think about the simple equation, the mathematical equation of attention QKV is equals to softmax of QK transpose, which is scaled, and then we put it into a softmax and then we multiply it with V. The entire thing is visualized here. So think about how good a visualization can be to convey or communicate the concepts. So it's not just a simple mathematical equation. It's a lot of things happen in between which we kind of not intuitively understand. So I hope we did a good job with the animations. Yeah, you can go ahead. And you are on mute, I think, Ritvik.
I'm sorry. I think we have a question about weight matrices are learned or not during training. Arthur, you want to take that?
Yeah, we do learn the weight matrices, and if we don't
Otherwise,
learn the weight matrices, it's
how will
always
you
going
learn?
to, exactly,
Yeah,
it's always going to give you same QKV, which does not make sense. So it's
exactly.
always going to be learned during training. Right, we can
Absolutely.
move ahead.
So with that, we are finished with attention, right? We started from passing a query and an input to f attention, or a function of function that computes attention, and from there we have come to this point where we have query key and value. We multiply query and key. We scale that product term, pass it through softmax, and then pass that out, or multiply that output with our value metrics, and we get our attention, and we are done with attention. Well, not quite yet, and there's just one little thing remaining. Remember in the beginning when we were showing you the architecture, and a lot of it wasn't making sense, a lot of it was skipped over. We were talking about something called masked multi-head attention. So that is, I'm sorry. Yeah, so that is what is left to cover. And before we go into the animation, because the animation is just going to visualize the concepts that we have learned or we will learn, but it is equally important to understand why we are doing it, the why behind it. So let's talk about the problem right now. All of this while we have been talking about, attention and evolution of attention and different parts of the architecture, but it is time to remember what all of this is for. Like, what is the task we are solving? Image classification, right? Got you. It's not image classification, it is neural machine translation. So the authors of the paper, attention is all you need, were actually solving the task of neural machine translation, right? And neural machine translation is the task of having one input sentence or source sentence, and then predicting a target sentence from it. Now, if we predict a target token in the decoder given a set of previously decoded target tokens and the input tokens, so you have an input that is being passed into the encoder decoder system, and the decoder basically decodes that based on the input, the current value of the input, and all of the previous target tokens, or all of the already decoded target tokens. So if you have I am a good boy, which Arthur would say he is, and then you have a translation of that sentence in French or German. Pardon me, I do not know much of French or German, so I wouldn't even try. But you have a similar translation of that
You can
sentence.
try in Bengali though.
We can try, and in Bengali it basically translates to আমি ভালো ছেলে, um, or আমি একটা ভালো ছেলে. And what happens is you have a certain on the basis of a certain position on the target token. So your translated sentence is your set of target tokens. So on the basis of that position, it will have already decoded tokens, so already translated words, and will have an input word from the source sentence, right? And based on these two, it will predict the next word. This is what a decoder does. Now, what happens, and this is a very interesting question, what happens if we use this attention, the previous version of attention that we just saw in the decoder? It has no way of hiding the future tokens or hiding the future words that it needs to translate from the decoder. So what happens? So let me ask you this in simpler terms. What happens to a student who is going to appear on a test, and he has practiced from a book which has all the answer keys, right? He will not have practiced at all. He would have copied everything from the answer keys, and on the test he would fail miserably because on the test he wouldn't have an answer key. And that is the same fate that lays ahead of our decoder. If our decoder already has access to the future words it needs to translate, then it won't learn, or it won't have the capability to translate. So what we need to do is the same thing that we need to do with a boy who has access to the answer keys. We have to hide the answer keys, or in the decoder we have to hide or mask the tokens that come afterwards. So this is the reason we need a form of attention that basically masks the future tokens or the future words that are going to appear to the decoder. And notice how I always mention that this is always for decoder. Only when you're decoding the source sentence into a set of target tokens is when you need the capability of masking. You wouldn't need it everywhere else. So Vaswani et al. Made this minute modification to the attention pipeline to accomplish masking before passing the scaled QK product term, so QK into 1 by root over of dimension, before passing that through a softmax layer, they would mask out certain parts with a large number, and that large number is negative infinity. And that going through a softmax will give you zero, right? Now, this is a minute modification that actually leads transformers working so well. And Arthur would tell you a story about how he missed masking parts of transformers, or masking parts of the decoder, or using masked multi-head attention, and it basically resulted in a disastrous result. So I wouldn't speak much longer. I'd much rather let the animation play out. And Arthur, if you have something you would like to tell our
Yeah,
audience.
I'm just going to comment. I'm just going to have a live commentary on our animations because we don't have that on the animations. So we start again with QKV, that is query key and value. We have a QK product, as we know, and then we what do we do? We use a scaled QK product, right? So we scale it, and Ritik is going to play the animation for that.
Yep, absolutely.
So, yep. So the QK product gets scaled with the root over dimension term. We get a scaled QK product. That is absolutely fine. And we need to stop here to understand what happens here. So I know it's kind of hard to see, but what happens here is that in the upper triangle of the matrix, we have negative infinities plugged in. So why negative infinities? And wh- so there are two questions. One is why is negative, and one is why is infinity. So it turns out that if you have a distribution and you plug in negative infinities to the portions where you don't really need to attend to, and pass that distribution into softmax, due to the way softmax is present, or the formulation of softmax, the negative infinities are exactly the positions where it turns to zero, right? It switches off. So hence we provide our negative infinities to the future tokens. And as you can see, if you think about it intuitively, the first time that we send an input, it is just the current state, and no other state gets to be allowed or gets allowed into the into the computation of attention. Hence, this is the first time it goes in, and all the other states, that is, look at the first row, it has just one yellow square, and the both other yellow squares are filled with negative infinity. And in the second step, in that is in the second row, we have the current step and the previous step and the future step as well. So the future step is something that we don't need, and hence there is only one negative infinity. And in the last stage, that is the third step, third row, we pass the entire input into it, right? We don't care about the future tokens because there are none. We have just the previous tokens, which is good to go, right? So let's play that. Negative infinity is going in into the softmax layer, and there you have it. The softmax is not really going to do just the softmax, but it's also going to turn off, as in switch off, the positions where the negative infinities were plugged in. Hence, you can see that the upper triangle or right triangle of the matrix being going to zero. Hence, these are the places where we need to mask the scaled softmax output into getting into the output value. So that is all that is happening. So the masking happens with the negative infinities getting plugged in, and everything is taken care of the softmax operation. And think about it, it's just something which I really like. They did not the authors did not really go into changing the entire architecture. They provided a simple hack. I would say it's a brilliant hack, nonetheless a hack, a brilliant hack into using the same architecture as is, but having certain things provided into the entire architecture or the entire module that takes care of what we really want, right? So the entire animation is very similar to what the animation was provided previously, just that negative infinities are plugged into the places which we want to hide, and everything falls into place as is. So yeah, that's about the commentary that I'm going to get.
And then finally, we multiply it the same way with value, and
Mhm.
we get our final attention output.
Yep.
And that's it. That's all that you need to learn about attention. I promise, attention no more. Now we move on to other parts of the architecture, but before that, we and you need a while to catch our breath. And
Yeah.
if you have any questions at this point, feel or any discussions uh, that you would want us to look at, then probably now is the time. Again, for people who are not PyImageSearch University members, and if you have a project that you have been putting off, or some project that you are on the verge of completion but not quite ready to finish yet, we think PyImageSearch University can help you out there. Um, with complete ready to go code. And all you need to do to get PyMessage University at a 20% off discount is scan the QR code that you see on screen.
Mhm.
And yeah, and don't put it off till tomorrow or till next week, because this is exclusively for people who are joining in and who want to get access to PyMessage University. Uh, so with that,
Right. And
uh,
before that, Ritvik, I'll just hop in. Sorry for interrupting. I'll just hop in and
absolutely.
say a couple of thoughts of mine, because this is the first time Pymate Search is kind of going into streaming, and we are no pro streamers or we are no YouTubers. We will have a lot of problems, and it's just beautiful to see that a community around Pymate Search is growing in YouTube itself. And I saw that people are really interested and they are questioning, and I also saw that many people are answering to the questions. So I really promote that. It's a place where you can comfortably share what you don't know and also what you know, and that people are respectful, and that is the best part about being in such a company where we always like people growing. So if you have anything in mind for us, recommend anything for recommendations in form of recommendations, that is what we could do, what we could better, and also some praises, because we like validations, as in this was a good stream, and we would like to see more streams from Ritvik and Orithro, and we are good to go. And yeah, those are the thoughts that were popping up. I just found it easy to talk it out open in the open. And I also see that there's a question. I was a bit confused between version 4 and version 5. Could you please link that to the animation above so that you can see? Okay, right. So
I
thanks
think
for the
it will
question.
get clear as
Yeah.
we move forward,
Mhm.
because
Right.
version 4 is more of cross attention and version 5 is self attention. And believe me or not, both of them are being used in the transformers architecture. So at this point, we have covered most of the important building blocks of the transformers architecture. Uh, the main part is attention, and attention holds together the encoder and decoder. You have specific forms of attention and not just basic self attention, but also cross attention, self attention, masked multi head attention. So all of these come together inside of transformers in the same architecture. But despite what the paper title says, attention is all you need. Only attention cannot create the entire model. And we need connecting wires to hold each piece together. So encoder, decoder held together by connecting wires. So we'll look at those connecting wires. But Arthur, you want to talk a little bit, and maybe I should go to this slide of the architecture or a previous slide of the architecture. Let me. So this slide of the architecture, and let's talk a little bit about the kinds of attention that is being used, so as
Right.
to clear up the query.
So yeah, let's go into this. And as you can see that in the encoder, the encoder gets an input, which is the input. Okay. So first let's go back. What is the one thing that our transformer architecture is going to solve is neural machine translation, right? And neural machine translation has input sentences and target sentences. So the encoder is fed with the input sentences, and the decoder is fed with the what do you call it, the target sentences. So I see Ritvik is not. I just want the slides to be yeah, thanks for that. So with the encoder and with the encoder gets the input sentences, the decoder gets the decoded sentences, the decoder gets the target sentences, my bad. Now, what happens is that in the encoder, the input sentences go in, and I'm not going into positional encodings and all that stuff right now. But can you see that in MHA, that is multi head attention, we have three prongs coming in? These are nothing but the query, the key, and the value, right? As Ritvik rightly shows. And where is this? What is the source of these three prongs? The source is the input sentence itself. Hence, we call it self attention, because remember, query, key, and value coming from one source is always self attention. It's in yourself. You look into yourself to get a better self. That's all I'm going to say. And then in the decoder stage, what happens is the first time the decoder gets the target sentences, it again, there are three prongs. The three prongs come from this unit source, which is the target sentences. Hence, again, a self attention. But what is added into a decoder is that MHA, that the second MHA, which is the multi-head attention, which gets the key and value from the output of the encoder, right? And the query is being fed from the target sentences that it get, like the output of the sublayer MMHA. So there is a distinct, partition between where the query and key come from, and where the I'm sorry, where the key and value come from, and where the query come from. I'm really sorry. It kind of is confusing to name all of the variables. So the query comes from the target sentence, and the key and value comes from the output of the encoder. And now, if I ask you what is it, it will be very easy for you to say that, okay, this is a cross attention, because we are crossing two paths. We don't have a single source from where the three prongs are coming from. We have two different individual sources from where the key value comes from and query comes from. So I think that would make sense to you, as in where we want self attention and where we want a cross attention. And I see a
Absolutely.
bunch of questions coming in. Cover masked MHA one more time. I'm sorry, James. I think we need to rush a little because we have taken a lot of time on scale softmax and a lot of that. If we have time after the stream, we will definitely come to your question and talk about masked. I'm sorry, about masking and the masked multi-head attention one more time.
Absolutely.
Right.
And with that, As I was saying, we like, even though we want um, only attention to be part of the architecture, it is not possible. We do need certain connecting wires or certain things that hold together. And so I'd actually hand it over to Orithro at this point to talk about one such connecting wire, which is called skip connections or residual connections. So Orithro, you me want to talk us through
Yeah.
that?
Yeah, absolutely. So anytime, Ritvik, you don't have to ask me this. If it's Transformers, I'm ready to speak about it. We can be friends if you want me to talk about Transformers. So yeah, the first connecting wire is skip connection. And why do we need skip connection? So as we in PyImageSearch quite heavily do is provide you with an analogy. If you understand the analogy, you will understand skip connection. So think about a PyImageSearch blog post. So it's a fine morning. You're with your cup of coffee or tea, whatever you prefer, and you feel like learning a little bit of computer vision, and you open pymagesearch.com/blogs, a selfless plug, and you see a blog post, and you start reading it. So what we kind of do is when we are going into a breakdown of a research paper, what we do is we provide the entire architecture in the very beginning of the blog post, and then with the sections coming in, as in when you scroll down, you read the sections, and you strip off a single part of that architecture. What we do is we refer to the entire architecture one more time, which is right at the beginning of the blog post. So you go up, you see which figure it is, where this section is located, and you come down again. So what eventually happens is we are kind of telling you, okay, this is the signal, this is the original signal, and you are trying to process the individual signals in in a later stage. But you also keep in mind that this original signal is something that you will need in different stages. So you have a better context, you have a better understanding of where this original signal is coming from, right? Now take this analogy to skip connections. What happens is, with every sublayer in the encoder and every sublayer in the decoder, the input sentences or the target sentences or the tokens for that matter get computed. Like the multi-head attention, the masked multi-head attention, and whatnot gets everything gets computed, everything gets processed. But with the residual connections or the skip connections, what happens is we are also providing the original inputs or the original targets to our encoder and decoder respectively at every stage outside of the sublayer, right? So that they have a more or a better context of what is being learned. So that is basically it. When you have skip connections, like in ResNets, residual networks, which formalized what skip connections could do. It's a brilliantly written paper. We have a blog post on ResNets. We have been using ResNets for quite some time. But coming from resonance to transformers does that exact same thing. We have skip connections, which also, if you can think about it, which it also helps in backpropagation, because in these skip connections you will not find any operation. That means the gradients coming from these skip connections are unaltered. They are absolutely untouched, and in the truest sense of the term, are just the gradients that we found in the later stage of the transformer architecture. So it's kind of very intuitive to think about skip connections to be a good highway networks, like in LSTMs. So there are a lot of analogies. I don't want to get into any of them. So these are like the highway networks that not only give you better inputs at a later stages, but also give you better gradients when you're backpropagating. So that concludes my
It is
entire. Yeah.
basically a way of referencing
Mhm.
your knowledge at a previous stage with your knowledge at a later stage, and that is what is happening in this connection. So if you see on screen, you'll see the residual connections uh, mm, marked with green, and what is happening is the inputs at certain stages or the outputs of certain stages are being fed back into the model at later stages, and what that does is it builds a richer or higher representation as the as the architecture progresses. So I think that covers skip connection. And we have yet another connecting wire that holds this architecture together, which is called feed forward networks. And they are present in both the encoder and decoder, as you can see on screen on with the yellow. And I'm not zooming in because it shows basically the same architecture that we have
Mhm.
been seeing on screen for the last 20 to 30 minutes. And the purpose of this layer is straightforward. The idea is to project the attention layer output in a higher dimensional space. This means the representations are projected to a higher dimension, and this is also the place where all of the inputs, like all of the parts of the inputs, are mixed together. So think of it as kind of your jumbo mixing bowl, where all of your ingredients are mixed together, shaken well enough, and then passed on to the next stage. What that does is that it allows your representations, or it allows your the learned representations to be projected to a better or a higher dimensional space. And you can see on the screen where it is applied in the transformer architecture. I see a lot of people are testing out the transformers from Google in the chat section.
Yeah, I was going to
uh,
come to that.
yeah,
It's really interesting. As in, giving a talk about neural machine translation and transformers in that section, and people are already using and
it
applying
in
that
real time.
in real time. That is so cool, right?
Crazy times. So the last piece of architecture that holds together this entire thing, and not exactly the last, you can kind of say penultimate, is called layer normalization. And with layer normalization, what happens is the normalization happens across the axes within each example, rather than across different examples in the batch. So in batch normalization, it happens across batches, but in layer normalization, it happens across the axes. And what it basically means that it is a row-wise operation and normalizes each row in the same weights. So in transform, not only in transformers but also in NLP tasks, the the normalization operation is basically a layer normalization. And we would really love to go into the different kinds of normalization. Why batch normalization, why not uh, batch normalization? But it is really beyond the scope of this particular tutorial. I would just like to say that NLP tasks or transformer tasks are more of sequential tasks, and thus they fit well within the definition of a row-wise operation
Right.
rather than a batch-wise operation. So let us know if you want us to cover the different kinds of normalizations and their applications. And with that, we are onto a very interesting slide and a very interesting part of the architecture. So, Arthur, uh, what exactly is positional encoding and why is it important? We
Right.
are pretty much done, right?
Mm-hmm. Absolutely. So, yeah, we are pretty much done. Thank you for the stream. Thank you for coming in, and we'll just take away. No, no. So this is an important part of the transformer architecture, and I can't stress on this enough, because this is not just a concept that you will learn, but also understand how attention works and how it does not help in a certain thing. So think about attention to be just this entire diagram that we went ahead with the videos as well. So attention cannot do one thing that a sequential or a convolutional model can, and that is to understand order of the sequences, right? I'll not go into details as to why it does not understand order, and we have a blog post coming up in a week time where we go into depth and details as to why the attention module does not understand order. But we are not going to cover it now. Just hold on for 1 week, and that's going to get published. Go into our socials. We are already active on our socials. We also send out emails to our PyImageSearch University fellows, and yeah, you will get to see a brilliant part written by Ritvik about positional encoding. So coming to that, we don't have order. Like the attention module cannot understand order. So if I say I am a good boy, which I am, as Ritvik has already mentioned. And if you jumble those terms and send that same sentence into the attention module, the attention module will not be able to figure out that the both the sentences are different, right? So they are not able to understand order. Now, Orithro, you have spoken about not understanding order for about 5 minutes straight. Give me the solution, man. Right. The solution is to provide each individual token with some information that it can go up with into the attention module. So this information is nothing but positional information. So if I tag I, if I tag am, if I tag a good boy, all of these tokens individually with their positions and with their relative positions or where they are meant to be, as in I gets 0, am gets 1, gets 2, good gets, you understand the sequence, right? So if you tag and label them and send that into the attention module, if you even jumble them and send that into the attention module will kind of understand that, okay, this token is meant to be present inside of the entire sentence, that is in the middle of the entire sentence. This token is meant to be on the left side or the right side of the sentence. Hence it understands the order, which makes it more intuitive, or the attention module under understanding order will understand that, okay, this sentence is jumbled and I need to unjumble it for that matter. It does not do it. I don't have a animation for unjumbling inside an attention module. It does not unjumble. I'm just giving an analogy as to what it does, what happens when you inject positional information. Now, that takes care of the first part of the term. So we have positional encoding. Position. Why do we need positions? Is fairly simple. And now we come to encoding. So, Ritvik, let me ask you this. We both understand a little bit about Boolean algebra. And the first thing that comes to your mind when when we see encoding and we see numbers, that is base 10 numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and onwards, what is the first encoding that comes to your mind, if I may ask you?
Binary. Zero zero
Exactly.
one 010.
Right. So if you go into the next slide, what we will see is that we have encoded certain positions with the binary encoding scheme. So 00001, 00010, and all that stuff, right? And I'll let this slide play for
Lingered for a
not
while.
play. Yeah, because this is going to be very intuitive when we move on to something that the authors have produced. So I'm not going to go into the code. The code is fairly simple. We just create n is the number of numbers, that is 0 to 100, that is the positions that we want to encode, and dims is the number of binary numbers. The number of binary numbers. Wow, you have piqued your intelligence, Orithro. So the dimensions of each encoding, right? So we have 0 to 100 as positions, and each of these positions are encoded into 100 dimensional vectors. And we
Absolutely.
fairly simply plt.im show it, that is we use this image and then show it off, right? And that is binary encoding.
And
Now,
just to
yeah, go ahead.
mention, the code is just for visualization purposes. What is more interesting is the representation of what that code is giving you, like the output, which is shown on the right, left.
Right.
I don't know how you're viewing your screen, but basically that green blob that you see on screen, that is where you need to focus your attention and think about what can go wrong here. Like we have as Arthur was saying, like we have input sentences. I am a good boy, Arthur is a good boy. We convert them into numbers, 0 1 2 3 4, and when then we convert those numbers into binary numbers, so 0 0 0 0 1 0, so on and so forth. uh, I am sure you would understand binary by now. But and and this is how that binary encoding or binary representation would look like for numbers from 0 to 100. So 0 to 100 are a fairly large number of, if
Positions.
you have 100 words, you have a big paragraph, right? So 100 words is represented in that square, or 100 words is represented through the violet markings on the left, and the rest of it is, I'd let the answer hang around in the air. And if anyone understands the problem here, I would want them to comment in the chat, because this is important as we move forward. I'm sorry, Arthur, you were saying.
No, so I was just saying that 100 is a fair, like, it's a big paragraph, but the main motive for me to use 100 is to get a good image in mind, because it's very difficult to have like a small little thing popping up in screen. So I used 100, and that is it. And yeah, absolutely, Tyler. That looks like a little fractal on the right, but it's not. It's not. It's just the binary encoding scheme that it looks fairly simple. And then we move on to the next slide and show our uh, what our what our paper, as in not our paper, was funny et al. Made in 2017. It is attention is all you need, and they proposed a sinusoidal and a cosine encoding scheme. And this function is something which they proposed. You will also find this function in the paper. I'm not going to dive deep into the function. We are more visual guys. So quickly going into the next slide, we will see that we have an entire code snippet written out to implement that encoding scheme. That is the sinusoidal encoding scheme. And the and we want your attention, one included and not included. We want your attention on the diagram itself and not the code, right? The code works. That is my guarantee. The diagram is something which we are going to focus on today. So that, can you see that the diagram is fairly similar to what we had already seen in the binary encoding, but there is a stark difference with this one. The binary encoding has a lot of zeros. That is, it's a very sparse representation, right? And as deep learning researchers, we don't want very sparse representations. We do want sparse representations in different architectures and specific architectures, but not in this case, because if you have very small signals like in binary encodings, and you inject that into your input, which goes into your transformer architecture, the transformer architecture is not going to do well. And the other problem is that with binary encoding, it's all zeros and ones, right? So it's discrete, it's not continuous. And as deep learning engineers, we love things which are continuous because it's differentiable, right? Backpropagation, remember, gradients. So what we do, what the authors do, is that they provide a sinusoidal encoding, which is not only continuous, it is also not that sparse. So I what we made is 0 to 100 positions with 100 dimensions, and the formulas that the paper has used, and we tried plotting it, right? And with plotting of this sinusoidal encoding, firstly, it's very close to what the binary encoding does. It just encodes the positions. But the two caveats that are included into this sinusoidal encodings is that it's not discrete, it's continuous, which is good for our gradients. And the other part is that it is not that sparse. So it does not have a lot of zeros, unlike binary encoding. Hence, we will go for sinusoidal encodings. And just to throw it out there, because we are all casually conversating, there what if we told you that there is a possibility of learning the sinusoidal encoding itself? It's let's not give static positions. We can learn that, and we will cover that in a blog post later. So it's just a good food for thought. Think about it, how it's going to, change the entire architecture or not, or maybe help in learning or not. So I'll just keep it to that. So
I would
sinusoidal encodings, yeah, go ahead.
I would also like to mention two things. Like there's a question in the chat which asks what happens when we add tangent and cotangent to such a scheme, which is
Mhm.
a natural question. We had all of these functions in trigonometry, might as well use them to put them to use, throw all of them in and see what happens. What happens is, see, the beautiful thing about sine and cos is that they are capped. Uh, what I basically mean is that they lie between -1 to 1. But with tan and cotangent, your domain goes from minus infinity to plus infinity. That essentially is a problem. You cannot have encodings, or you cannot have representation of your input flowing from minus infinity to plus infinity when your input itself is bound within 0 to n, where n is your vocabulary. So that is a problem. That is why we cannot use tangent and cotangent. There is also another reason why we use sine and cos, and I would like to draw your attention to my hands at this point, because I do not have a meme animation, but I do have my hands, thankfully. So this is what a sine curve looks like, right? Now, if a sine curve looks like this, at any point in the curve, at any point in the wave system or in the system, you will be able to draw a line from the origin, or draw a line from any point on your Cartesian axis, and get to that point on the wave. So your position, or your offset position, is always a linear distance away, and that can be learned. And why can it be learned? Because sine and cos tend to repeat themselves after a certain point of time, right? So this is something that the authors have also put in the paper itself, that it's always basically offset by a position of k, and that k is um, that k is a linear distance. um, with that, we come to an end of positional encoding, of encoding inputs into the transformer architecture in a special scheme that actually helps the architecture, that actually helps learn better than binary encoding scheme, because it is not sparse. It is densely filled, as well as it is always offset by a position of k, which is linear. And that is it. That gives us all of the components, all of the pieces inside of the transformer architecture, and we are finally at an end of our entire slide, where we talk about transformers. Arthur, do you have anything in mind that you would like to tell people at this point?
Right. Just a little thing is that, remember when I started speaking, I said that um, this architecture is not going to make sense right now. We have a lot of jargons, and I'll ask you right at the end of the slide, does this make sense now? So I'll keep my promise. So I would love to see people interacting with us. So does the architecture make sense now? If it does, throw in a thumbs up. If it does not, look into the recording again, because it's going to stay in our PyImageSearch channel. So look into the recording again, take notes. If you have, like, if you are seeing this 1 week or 2 weeks later, go to pymagesearch.com/blogs. You will find our part 2 for the entire thing. And yeah, and Ritik has also linked to our Twitter handle. If you think you want us, you want to be up to date with all the blog posts that we share it on our Twitter handle. We also share a bunch of other things on our Twitter handle, mostly deep learning. So do that. And I also see a couple of questions. Why don't we scale after this? Okay, James. So are you talking about the QK, that is the square root dimension that gets scaled it with? So I'm now talking directly to James. So I'm also going to take another question until and unless James answers to that. Uh, you can learn from sequences of images, like the example video captioning. Yes, that transformer is called vision transformer. And if you
No, I
want to
think
talk,
they mean not just images, but sequence, like a stream of images.
right, you can quickly go to, at the top of my head, you can quickly go to video MAE, that is video masked auto autoencoders,
Yes.
which can process videos. But for video captioning, you also need another modality, that is text. So I am not sure how both of them are going to work together, but if you go into archive and look up
So
into
there's
it,
a Keras example from Audithro himself, and he's just being humble where he's not talking about it, which is video vision transformers. And you can look into that as well for this. But again, for people who are just here for transformers, beyond the scope of this, we are just talking about these because we have completely ended our live stream. And yeah, sorry, Arthur, you're talking about talking to James or
right. And James says yes. So James, what happens is, if you scale the QK product, after you go for your entire softmax, it defeats the purpose, right? Because the softmax is where you want the softmax to not be just one peak. You want the other small peaks to come in. And to make that happen, you need to scale it before it goes into softmax. That is the QK product. So hence we take our QK product, scale it, and then pass it to softmax so that the peaks are more distributed to help the model get the gradients back. So I think that kind of covers the question. And
so.
another simple thing, sorry, Ritvik, before saying, uh, about the video vision transformer, it is again the same thing, because it's not going to cover image captioning. It's going to process the videos in tokens and all that. So you can definitely check out that example, but you also need to understand a different encoder architecture that takes into account this modality of text. Hence you process the video at one go, the text at one go, and then combine them together to get the video captioning working. So I hope that makes sense. And James says, I'm talking about the after the product with V. I am not sure if I understand it correctly. So Ritik, you can go ahead with the slide. James, I would just think if you could elaborate the question a little better.
Yeah, right. So, like, I would like to draw attention to some of the references that we have used. So, of course, the original paper, which is Attention All You Need. We also have the evolution of attention as you know uh, as we show on screen. The animations and the visualizations were built using Manim Community Edition, which is a Python library for math animations. So great, uh, grateful to all of these resources for helping us put this together. And with that, we actually come to an end of this live stream. So thank you for joining in. Again, um, something this live stream will be there. It will be recorded. You will be able to come back here, comment, or take notes, pause, do whatever you want to. What will not be here is this link that you see on screen, and I will actually post this link in the chat down below. Will be saying this again. This is for people who have not joined PyImageSearch University, or who are just on the fence of joining PyImageSearch University, who are thinking about finishing up their project or having a Transformers project completed, but they are not, for any reason, not being able to do that. We think PyMessage University will help you a lot. uh, we do, because we are a tiny bit biased in creating that. But again, we receive that, uh, we get that as feedback from our students, from our alumni, who continuously tell us that PyMessage University was a boon to them. It helped them a lot, um, getting a job, landing a research paper, and whatnot. We think you have been with us for a long, long time now, and you deserve something in return. So you get 20% off um, uh, on PyMessage University, and we get hopefully your praises. Just kidding. If you have any constructive feedback, do post it in the chat, or tweet to us, and we will look into it. But for the time being, if you are on the fence on PyMessage University, get it for 20% off. Get it now, because it won't be available tomorrow, or 3 hours from now, or the day after. And we do have a 30-day money back guarantee, so you wouldn't have to worry about not having the best fit course that you need. I hope we made transformers a little bit clear. We were able to share some intuitions that you did not have, or that were not available previously. So that is our hope. I genuinely think that if there is something lacking, if you could not understand anything, write to us in the comments or in Twitter, and we will try our best to answer that. And do let us know in Twitter, as well as in our social media handles, as well as in YouTube, what other kind of live streams would you want. This was Transformer. It was one of the hottest topics right now. But what else would you want? What else do you want from us? What else do you want from PyMessage? And what else do you want inside of PyMessage University? So thanks a lot, guys, for staying with us. Our spaceship has finally landed, and we are at an end of our journey through the land of attention. Arthur, do you want to say some parting words?
Parting words, and before that, I see. I'm really sorry, Ritvik. I just see this question from James coming in. So James, a 1 minute answer quickly. QK by root square root of dim of x is because that square root of dim of x is the standard deviation of the dot product of QK, and you can't scale that entire softmax with another square root of dim, because that is not the standard deviation of the entire distribution. For that, to normalize it, we use layer normalizations, as Ritvik said. So I'm just going to leave it there. If you want to take this question up further, tweet to us, write to us. And also, just to let everybody know, PyImageSearch University students have this open access to us by chatting to our customer support, and they kind of tell us that these students need an understanding of this blog post is good, this blog post is not, and we take constructive criticisms. So why not join it and talk to us there? So yeah,
Absolutely.
that's about it from my
And do
end.
let us know about uh, yeah, the subscription gives you all the courses. We wouldn't give you 10% of the courses and then 90% later on. It gives you all the courses upfront. And actually, this was a course on transformers
Mhm.
that is yet to be released. So it is for our YouTube community, exclusively for you guys. We know you are special. We know that you stick with us for so long.
2 hours.
So 2 hours. So why not consider joining us permanently? So yeah, that with that, I hope you enjoyed it. Do let us know if you did or didn't. And thank you again for joining in. Live and prosper.